Hello everyone. Let's see how to plot math functions using geometry nodes. This functionality is already included in my Bezier toolkit add-on, but here we will see specifically how to do the same thing using just the geometry nodes without any add-on. I have uploaded the files we create here on GitHub. The link is in the video description. There are primarily three forms in which math functions appear: the Cartesian form, the parametric form, and the polar form. Let's start with the Cartesian, as it is the more common of the three forms. In Cartesian form of a math function, y is described as a function of x. For example, Cartesian equation of a line is y equal to mx plus c. That of a circle is y equal to square root of r square minus x square. And that of a parabola is y equal to x square plus bx plus c. Let's first plot the line math equation using the geonodes. So I'll open Blender and go to Geometry Nodes workspace. Create a new Geometry Node setup. We'll first add a curve line node. And let's get the length of this line from group input. Next, we need to separate out the x component from the position. So first we'll add the position node and then a separate xyz node. So at this point we have the x component separated and we will calculate the y based on this x. Ultimately we want to combine all these three into a single vector. So I'll right away add a combine xyz node and connect the x and z sockets to the combined xyz. Only the y parameter we will be calculating based on our x value. This combined xyz will be fed to the set position node of the same geometry. So let's have the length as 5. Currently we are not changing the y value, so it will be a flat line along the x-axis. Now let's calculate y. It's basically mx plus c. So we need to first of all multiply the x value with the slope, that is m. Let's get this from the group input. I'll call this slope, or let's say m. We have the mx part ready now. I'll just add a math add node, and to this mx we will add c. We got our y value, and if we feed it to the y socket, we get this line which is defined by the equation mx plus c. If I change the slope, the nature of the line changes, and I can also change the y offset by changing the c value. Let's convert this to a parabola now. We just need to change this equation. The rest of the things will remain more or less the same. First, we'll remove these group inputs because there will be new inputs now. You remember the equation of the parabola is y equal to x square plus bx plus c. So we need a, b, c. And the resulting equation won't be a simple line. It will be a curve. So we need more resolution to this line. First of all, let's add a resample curve node, which will allow us to define more resolution for this line. I'll remove these group inputs and create new ones. Firstly, let's have resolution. Then let's define start and end for the line, or rather the curve. This will be our start, and this one will be the end. Now we will change the actual equation. I will maximize the window. So So the equation is basically ax square. So we'll first of all take x and square it by raising its power, then multiply it with a. Let's take the value of a from the group input again. So we have ax square now. We need to add bx to that. So I'll have another multiply node and multiply the x with value b, which will again be coming from the group input. And we need to add these two values. So I'll add a maths add node and add x square with bx. And finally we need to add c to this. So I'll duplicate this add node and get the c from the group input and add the result of the previous node to this socket. Finally, the value we got by calculating the result will go into the y socket of combine xyz node. Let's also change the group socket names. This is our A, this is B, and this is C. Let's define the start and end values. Let's say -1 and +1. So you see now we have a parabola. Let's set the C value to 0, A value to 1, and B value to 0. So it will be symmetric around the origin. And now if we change the values of these parameters, we get a different curve. Similarly, you can also create a circle and other equations that involve the Cartesian form of equation. We'll quickly see how we can create the circle. For the circle, we don't need ABC, so I'll remove these group input sockets. And we just need the radius, which we will add a little later. Now, let's redefine the equation. The equation is basically square root of r square minus x square. So let's get the r from the group input and raise it to the power of 2. I'll call this r or radius. We have r square now. Let's also square x. And let's subtract x square from r square. And take the square root of this value. Feed it to the y socket of combine xyz and increase the r value here, let's say 3, and the resolution. I just need to set this value to 2, and we have got the semicircle now. If you look at the equation of the circle, it's actually y equal to plus or minus square root of so and so. So basically we have got the plus part now, and we need to also plot the minus part of the equation. For that we need to duplicate all these things and we need to create another curved line. I just group these nodes and call it semicircle. We'll just add one value to this and use that value to multiply the end result. This value will basically determine whether it's the top part or the bottom part. If we put it as 1, it will be top, and if we put it -1, it will be bottom. So I'll just get this value from the group input and call it coefficient. Now let's duplicate this group node, and first part we will feed 1 into the value node or the coefficient node, and for the another The rest of the things will be the same, only the coefficient will be -1. Let's duplicate the set position also, connect the geometry and position, and finally we will have a join geometry node to join these two parts. So we have a circle now, and the radius of the circle can be changed from this part. Now it's fairly easy to get rid of these extending axis lines. All we need to do is, instead of getting the start and end values from the group input, we need to calculate them based on R. So I'll just remove the start and end sockets from group input, and for the end value I'll simply get R because it's extending by R on the right hand side, and for the left hand side I'll simply multiply R by -1, and the same thing we will feed to the other semicircle also. And now we get a perfect circle which can be controlled through radius and which is created based on a math equation using geonodes. In the next part we will see how we can plot equations of the parametric form. If you have any queries or suggestions, please write in the comment section below. Thank you very much.